All right, so we're talking about polynomials. And which of the following are polynomials? I gave you a little preview of this the other day, and I said that the powers couldn't be fractions and the powers couldn't be negative. So this guy's clear. He is a polynomial, and so is this. Even though there's only one term, it is a polynomial. Polynomials can have as little as one term. It wouldn't be much point if it didn't have any terms, then it wouldn't exist. So this pretty much spans the gamut of polynomials. This is not a polynomial because of that fractional exponent. That does mean x to the 3/4 means like this, which I could break up as x to the 3 times x to the 1/4, which means x to the 3rd under a 4th root sign, in case you hadn't seen that in a long time. Don't worry, that's not important yet, but I'm just trying to remind you that the x to the 3/4 is kind of weird, and that's what disqualifies it from being a polynomial. And this one's disqualified because that, when the x is in the bottom, what does that mean? X to the -1. And if it's x to the -1, this would mean 3x to the 3rd minus 7x to the -1 plus 10. That's not allowed. Can't have negative exponents. Okay, so that's not a polynomial, and neither is that. That reminds me of a joke. I'm not a schizophrenic, and neither am I. Okay, anyway. Schizophrenics often have, well, anyway. Okay, if you don't get it, you probably, that's all right. Determine the degree of the polynomial. All right, this is a 3rd degree because its biggest degree is a 3. This one has a degree 2 term in it. That's degree 2. That's degree 0. A lot of people think it's degree 1, but it's not. It would have an x there if it was degree 1. But if it's got an x to the 0 there, an imaginary x to the 0, that could remind you that it's degree 0. All right, so degree 0, degree 2, and degree 3, this one wins. You don't like add them up. It's just the biggest degree wins. So that is a 3rd degree polynomial. All right, this one down here, if I multiplied it out, it would be x squared. The -2 and the +2 would cancel, and then I'd have -4. Now, can you see it's degree 2? Yeah, so this is degree 2, even though you don't see a squared anywhere in it. It's an important thing to note. So you could have thought of it as that's a degree 1, that's degree 1, put them together, it's degree 2. That'll help you when you do this one. This one's degree, take a wild guess, degree 6. I know you're thinking it's the biggest one, but if I multiplied this all the way out, I'd have an x to the 6th in it. And therefore it's 6th degree. All right, so that clears up stuff about degrees. Remember on end behavior, the ends, there's the left end and the right end. And it's either up or it's down. Okay? So the end value on this is down on the left and up on the right. Down, up. Don't get confused by thinking about is it increasing or decreasing. That's totally different. It's down or up. What's that? Up, up. What's that? Down, down. What's this? Up, down. All right, now let's start talking about limits for just a second. A limit would mean where is it going to eventually go to? If I go this way forever on this graph, if I go this way forever, it would have a limit of -infinity. That's where the function would kind of end up if I moved way over this way. Do you get if I would go way over this way, the function would have a limit of +infinity? Okay, we'll talk more about that later. I'm just doing a little preview there. Okay, this one is what for the end values? Down and up. And the last one, down, down. All right, how can you tell by looking at an equation what the graph's going to be like? Whether it's going to be up, up, down, down. Well, here's something that you know. You know x squared, it looks like this. You know negative x squared, it looks like that. And remember that the ones that are even degrees, like degree 2, degree 4, degree 6, they all go together. They're either both up or both down. Okay? So like look at degree 4 stuff. They're both up, both down. Degree 6, don't have any. But if I did, they would either be both up or both down. Okay? Degree 2s, 4s, and 6s, they all go together. Odd ones are apart, like this. This one's an odd degree, and notice one's up, one's down. One's up, one's down. That's odd. And when I go to degree 3, one up, one down. One up, one down. All right. How do you know which way to go then? Well, that lead thing, this number in front, if it's negative, that tells you the right-hand side is down. That only tells you the right-hand side. So once I know that's down, then if I know it's odd, I know they're going in opposite directions. For instance, let's say I said this, negative 16x to the 15th. Tell me, do both ends go up, do both ends go down, or do they go opposite directions? They go opposites because it's odd. Then you really should decide first the right side. What does that tell me? Right side is down. So therefore, if they go opposite directions, the left side must be up. All right. Take this short little 3-question quiz, and all you need to say is left is this and right is this. All right. Is the left end of this up or down, and is the right end of this up or down? Don't say it. Write it on your paper. Number 1. Left is, right is. Number 2, I'll give you a simpler one. For those of you that can't handle that first one. What's the left side doing? What's the right side doing? And the last one will be a stretcher. If you haven't answered number 1 yet, you're probably not going to be able to. I'm moving that up. Who feels pretty confident they know the answers? All right, good. A few confident people here. Number 1, on the right-hand side. Well, first of all, I should find the lead coefficient. Is this really the lead coefficient? No, it's not. Because this is. Because this has the highest degree. This is a degree 200 polynomial. It's an even one, which means that they're either both up or they're both down. And this one, this negative here, on the lead coefficient is negative. That means that it's going down on the right. And then if I were to pick, since they have to both be going together because it's even, then I have to say this also is down because it has to be the same. Down, down. Raise your hand if you had that one right. Good. Next one, the left side. Oh, first of all, I should really do the right side. This is the lead coefficient this time, and the right side goes based on whether this is positive or negative, and it's positive, so it's up. And since this is even, they both go together. Up, up. Raise your hand if you had that one right. Good. And did you know that the last one is not a polynomial? Good. This one is makes it pretty obvious. And last hour I put it like this, and almost nobody caught it. I said 2x to the negative 7th. And they just thought of, well, which is the biggest number to tell which is the lead coefficient, and they kind of glossed over this. If I had done that also, you'd say, not a polynomial, therefore I don't have to answer. Okay. Moving on. To sum it up, the lead coefficient tells you the right side, the right end, is either up or down. And the degree tells you whether they're both up and down, like whether they both go together, whether they are opposite of each other. All right. This is just a 2-second little fun thing of, there's this little graph maker that if I mess with this is the lead coefficient. As I make it bigger and bigger, see how it's getting stretched? It's almost like somebody's grabbing it from up above and pulling on it, and it's getting tighter and tighter. And if I go back down, it's loosening up, and the number in front is getting smaller and smaller, and it just gets looser and looser, and eventually, it flips upside down. It's because it went negative. Okay, so if the lead coefficient goes negative, the whole thing flips. All right, so let's get back up to here as a normal parabola. That spot where it was a flat line was because the whole x squared thing went away and it wasn't quadratic anymore. If I make this 0, see how it doesn't have a lead coefficient anymore? Or it doesn't have a x squared term? That's why it turns into a straight line. Okay, anyway, this one, if I change this, it's kind of weird. It makes the whole thing kind of like shift up, down. It's the middle number, the thing on the x. I can't really describe terribly well what that does, but if you watch just the bottom of the parabola, the vertex of the parabola, watch where the vertex goes. Do, 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 do. Do, 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 do. And then it goes around the horn. Do you see what the vertex is making? A parabola. See how the vertex is making a parabola? Okay, that was somewhat interesting. And then, if you go to this and I make it have an x cubed in it, now this is a cubic. But you might say, wait a minute, Mr. Server, you've told us that they're supposed to have 3 roots, but this only has 1 root. It has 1 real root, and what are the other ones? Imaginaries. Okay. If I change this so that it's up to a, let's say it's like cubic, so it should have 3 roots, and then I mess with one of these other terms, I can make it come up and have 3 roots now. See? Now it's got 3 real roots. There and there and there. So it's got 3 real roots now. But the other kind still had 3 roots. It was just that one of them was real and 2 were imaginaries. If you ever have imaginaries, they're always in packages of 2. Remember the quadratic formula? It says plus or minus the square root of. When do you ever have an imaginary? When there's a negative under that square root. So if there's plus and a minus in front of it, that means there's 2 roots. They're always going to be sets of 2. All right. Some other stuff from HA that you learned last year. Increasing, decreasing. The end behaviors, we just talked about that. Okay, so this part right here, would you agree that that is increasing as you read from left to right? So we'd say that is increasing between 1 and 3. 1 to 3. You put parentheses around it because it's not actually increasing on the end points. Remember that? Is there any other spot where this thing is increasing? No, it's only going down in the other spots. So it's going down from here to here, and that's from way over here up until there. From negative infinity to 1. The other spot, I so often see this one wrong. It's decreasing, it is decreasing in here, but kids will write from 3 to negative infinity. They're wrong, but can you see why they would think that? Because it's going down to negative infinity, but that's not the question. The question is, it's decreasing from here to, well, where do you put that other line? Way over that way, which is positive infinity. So it's really decreasing from 3 to positive infinity. Put it there. End behavior. That's a really simple question. Don't overthink it. Is it down, up, down, down, up, down? What is it? Up, down. Up is first because it's on the left, and then down. Because it's up here and it's down there. Okay, local minimum. That's the locally the low spot. In this graph, that's kind of the low spot. I see you put it on my desk. Yeah, you. Unless, yeah, that's what I thought. Put it on my desk, please. Rapidly. Don't waste my time. Okay. Was there somebody else that was going to bring up something because they thought they got caught? Okay. Anyway, local minimum. This is a low spot. That's the local minimum. This is a high spot. That's called a local maximum. Can you be a local high spot and also the highest spot of them all? Yeah. Like locally around here, the high spot is there's a spot on, I think it's at Lutsen. It's the highest spot in Minnesota. Okay, you know where Lutsen is? Way up north, it's a ski hill. It makes sense it would be a ski hill if it's a really high spot. The low spot, I think, is down in the southeastern part of the state. But our local high spot and local low spot are not the highest spot in America or the lowest spot in America. In America, what you know what the lowest spot is? Death Valley. Yep, Death Valley is the lowest spot. It's way below sea level, and so that's locally a low spot, and it's the lowest spot of them all in the United States, anyway. In the world, I'm not sure where it is actually. Is it the Dead Sea? Interesting. All right, cool. Then there's the highest spot in the world, which I believe is the top of Mount Everest. Okay, so that would be locally a high spot, and it's the highest spot of them all. But there is an argument about that one, just so you know. Some people say on the top of it, the island of Hawaii, one of the islands in Hawaii, I think it's the Big Island, has a mountain on it that is the highest spot in Hawaii. Well, why would that possibly be the highest in the world? Because if you go down into the water and you find the base of the mountain, which is way down, like miles below the ocean, and you start there and you go to the highest spot, it's actually taller than Mount Everest is. Isn't that interesting? So in other words, Hawaii, where, let's say this is the island of Hawaii sticking out of the water. The water's like this, and here's the island of Hawaii way up on top of that. If you measure from down here to up here, it's taller in Hawaii than it is from the base of Mount Everest to the height of Mount Everest. Okay, anyway, if I have, I'm going to one more like this. This spot here, that's called a local maximum. True or false? True. It's also called something else. What? Absolute max. How about this spot? Local min. Is it the absolute min? No, because the lowest of them all is not known. There is no minimum. And then this, what's that spot called? It's a local max. All right. Back to our list of things you got to know. Increasing, decreasing, talked about that. End behavior, up, down, talked about that. Local mins and maxes, we just talked about that. The absolute mins and maxes, it depends on the graph. A lot of times they don't have one because they're going to infinity. Extremes are just like the low spots and the high spots all put together. Those are extreme spots. They're either high spots or low spots. Those are the extremes. The roots are the spots where it touches, like right there and right there. Those are important spots. Let's zoom in on a few of those. Let's say the graph did this. Do you remember that that's a bounce and worth 2? Do you remember this is a cut through and it's a degree 1? And you get how together this is a 2 plus a 1 makes the whole thing a degree 3? Does that ring a bell? And does degree 3 make sense because it's going up there and down there? Yeah, degree 3 makes sense for this. All right, I'm going to give you a couple graphs and see if you can write me the equation for it. Here's one. It's got 2 roots. One's here, one's here. Do you remember how to write equations for these? If you don't, I'll help you with this one, and then I'll have you do another one. Okay, I say y equals, and then I put a parenthesis, and then I say negative 3 is the root. So then x plus 3 would be the factor that goes with that. And then x minus or plus 1 would work for a negative 1. Because if the negative 1 goes in there, it would make the thing equal 0. Does this ring a bell? You remember writing equations like this? For graphs? I know you did it in higher algebra. Even not HA9 did really, actually I think HA9 and HA regular did the same thing on this. You learned this. If I multiplied this out, you might recognize it better. X squared plus 4x plus 3. That looks like more of a normal quadratic. But now you might say, wait a minute. That one has a y-intercept of 3. But this one's y-intercept is actually 6. There was a stretch. There was a stretch going on. So actually, that means that this thing must really have a 2 in front of it. And now if I multiplied it all out, I'd have x squared plus 4x plus 3, but times everything by 2. 2x squared plus 8x plus 6. And now it actually matches up with my graph because the y-intercept is 6. All right, I'll give you another one. That one. See if you can write me the equation for that one. You need this to come back now because this is your next test. It's got this stuff on it. Well, you zoom in on the roots. You do y equals. of course, start an equation. Then, for the 0 one, you could say x, and you could say plus 0 or minus 0 would be fine. Because when I put in the 0 into this, it's supposed to make it equal 0, and so now it will. The other part, that's a 3. Do I say x plus 3 or x minus 3? Minus 3. That way a positive 3 could be put in here and make this equal 0. Okay? What's one more thing, though? It's squared, because remember this is a bounce, so it's worth 2, so you put that there. There's your answer. Could it be stretched and we wouldn't know it? Yep. If you want to acknowledge that, you can put an A here and say, I don't know what the stretch factor is, and that's good enough. Now, is it going down on the left or sorry, on the right? Ah, if it's going down on the right, what does that tell me? That it must be negative. So then it'd be even better if you threw in a negative here. And then I don't know if it's been stretched or not, but there could be a number there too. Okay? All right, here's another one like that. See if you can handle this one. Y equals, give me the equation. It's really not that hard. Okay, got two sets of parentheses for the two roots. One of them's at -1, one of them's at 3. And that'd be x plus 1 and x minus 3. Right? Wrong. What am I missing? A squared on which one? The plus 1. Because this is a bounce right there. So now, does it make sense? This has degree 3. There's a 1 there. Degree 3 should be going opposite directions on its ends. Is it? See? It's going down. It's going up. It's degree 3. Makes sense. All right. Is this coming back? Are you remembering this? Good. Okay, this next part. What are the zeros of this? They're here, and here, and here. Those are the zeros. They're also known as the roots. They're also known as the solutions. They're also known as the x-intercepts. They're really important points. They have 4 names. Roots, zeros, x-intercepts, solutions. Okay? What's that spot called? Absolute max. And, wait a minute, not the absolute max. Because see this? It's going to go up. It's going to keep going up. So is that. You can always assume there's zeros in the ends of those. If you don't know for sure on a test, you can always ask. So it's not an absolute max, but it is a local max. How about that guy right there? Local min. All right, good. Okay. So now let's get to limits. That's the last thing I got to teach you for today. Limits. We're just introducing you to them, just giving you the idea of what they are. They get much more complicated. In calc, you spend like a month on limits. Okay, you're just in pre-calc. We're just going to learn the basics today. We go into a little bit more advanced ones tomorrow. All right? So here's limits. The limit of this function. Limit of f of x. That means limit of the function. When you think of limit, don't you think of like the highest you can go? Or the lowest that you can go? Or like kind of like what something ends at? How about this? Do you know that in the United States, if you are a pilot, that the oldest that you can be and be a pilot of a major airline, do you know that there's a cap for that? Like when you hit that age, you're done. Even if you're the best pilot they have, you're done. Automatic out. I think it's 65, but I'm not positive. Is it? Oh, there you go. 65. Okay, so he could be a highly paid, very skilled pilot. He could still be awesome at his job, but if he's 65, boop, you've limited, you're done. You have to retire. And you can go do other things, but you can't work for the big airlines as a pilot. Okay, so that's a limit. It's like where it stops. Okay, this one, do you see how this function, as I move farther and farther, that way it's just going to get closer and closer and closer to 1? Its limit is 1. Going that way. That's what we call the limit as x approaches infinity. What that really means is the limit going this way. The limit going that way is 1. How about this limit as in going this way? Do you see how it's getting closer and closer and closer to 0? So the limit as x approaches negative infinity is this part. The limit as x approaches negative infinity would be 0. As in, it stops at 0. It kind of limits out there. The other way, it stops at 1. All right, let's look at another one. The limit of this one as x approaches infinity. When they're talking about this, they're saying going that way. Going that way, what's the limit of this thing? 0. That equals 0. The limit as x approaches negative infinity, this one right here, is going this way. If you go that way, what's the limit? 0. It's kind of like asking how big the y is, because see, x is negative infinity. It's like how big is the y value of it when I go way over here. All right, let's look at some more. Look at this one. This is a classic function, the e function, the exponential function. It's one of your 12 big functions that you are supposed to have learned. And I know some of them are still rusty, like this one. Okay, so this is the exponential function. And as I go forever this way, what's the y value going to become? Infinity. As I go forever this way, what's the y value going to be? 0. You getting the idea? All right. Let's say we had a function that did this, and that dotted line was at 8. How would you describe that end over there? How would you say it with a limit? The limit as what? X approaches infinity of this function is equal to what? 8. Because the highest it's ever going to be is 8. How could I describe the left side of this graph? The limit of the function as what? X approaches negative infinity, that's this end of the graph, would be what? Negative infinity. That's the basics of how to write a limit. Yes? That's a clue that it's probably going to be the limit of it. All right, I'm going to give you one more. I want you to see I'd like you to tell me the limit of this function as x approaches infinity. Oh, I forgot the function part. Write it down in your paper. Now here's the tougher one. What's the limit of this function as x approaches negative 7? So this first question was just, if I go forever that way, how high is it when I get there? 0. Raise your hand if you had 0 for that one. Good. This other one, the limit of the function as x approaches negative 7. Why didn't I just go to infinity? If I go over that way, there's nothing there, is there? See what I'm saying? If I go way over there, this isn't going to ever cross the dotted line because it's an asymptote. So I don't want to do the limit as x approaches negative infinity because there's nothing over there. But I could do the limit of the function as x approaches negative 7. But do you agree that I could approach negative 7 from either this side or I could approach negative 7 from this side? So they have to tell you which one they want. The one approaching from this side means nonsense because there's nothing over there. It's undefined. But the limit as x approaches negative 7 from the positive numbers, which were over here, you'd put a little plus here. And that means I'm approaching the negative 7 from the positives. Then my answer has a possible meaning. If I'm going from this side, where is my y going to as I get closer and closer to negative 7? Closer and closer. It's getting higher and higher, isn't it? What's the answer? Infinity is right. All right, so let's look at another one. This one, the limit approaching 0. Do you get that I could go towards 0 from this side and have an answer of negative infinity? Do you get, if I was approaching the 0 from this side, then I'm going to have an answer of positive infinity? That's why we have this little plus and this little minus. This one's the limit as x approaches 0 from the negatives. That's from over here, heading that way, approaching 0. Then they're talking about this line right there. Negative infinity. The limit of this one as x approaches 0 from the positives. Okay, so that's saying if I'm over here and I'm approaching 0, I'm getting closer and closer to 0, which is like right here. I'm getting closer and closer to that, then I'm going to get sucked into this one. And I end up at positive infinity. All right, it's a lot for a Monday. Here's a typical problem. Y equals x cubed. Tell me its limit as x approaches infinity. Well, all you got to say is the limit of this function is, if I go forever, here's a little sketch of it. If I go forever that way, I already know the x. The x is infinity. What's the y going to be? Infinity. And how do I write the left end of it? The limit as of x cubed as x approaches the left side is negative infinity. That means if I go forever this way, then the y value would be negative infinity. All right, I think you're getting the idea. All right.